The following theorem says that the operator Jn converges to a partial differential operator as n tends to infinity. Let us state the theorem for every h in C12. This means that h is one time continuously differentiable with respect to the time t, and h is twice continuously differentiable with respect to s. So remember, Jn is an operator which operates on functions, right? In particular, we are operating it on the function which we obtained as the price of our option through the binomial model. Okay, basically h is a function depending on two variables t and s. This theorem assumes that h is once continuously differentiable with respect to t and twice continuously differentiable with respect to s. If you take such a function and you operate Jn on such functions, if this happens, then only this theorem happens. Okay, divided by n, and that for all t and s, if you take and divide that by n and take limit n tends to infinity, then this will lead to another operator which we call as LBS. Again, that operator is operating on h of ts. Okay, and now what is this operator? It is called the Black-Scholes operator, where LBS is an operator which is operating on a function h, gives you dou h by dou t plus sigma square s square by 2 dou square h by dou s square plus or s dou h by dou s minus, or if you want you can put the argument everywhere, t comma s, t comma s you can put everywhere. Often we don't write the argument t comma s, we just write the expression, and this is called the Black-Scholes differential operator. So this theorem shows that your discrete time binomial model is actually tending to this operator, differential operator. Let us try to prove this theorem using 2D Taylor expansion of HU. Let us first take HU, then we will take HD, and then substitute back into H. We will get this expression. See, you have H is defined in terms of HU and HD. Remember, HU is given by this expression, HD is given by this expression, where T is perturbed, T plus delta T, and S also is perturbed, SUN. Okay, from S you went to SUN here. So there is a variation in S as well as there is a variation in T. Therefore, there is a variation in both the variables of h, that gives you HU. Therefore, you can apply the Taylor expansion for both the variables. HU of t comma s is actually defined as h of t plus delta tn comma sun, right? And that can be written as h of ts. So you have to apply the Taylor expansion in each variable and then the mixed also. That is what is 2D Taylor expansion. You would have studied it in your real analysis course. You can recall that, or in calculus course also you would have studied dou h of t comma s by dou t delta tn. This is the second term in the Taylor expansion as far as the t variable is concerned. Similarly, you have to write the second term, that is the first order term, in with respect to the s variable. S variable is what? It is sun minus s, right? That can be written as s of un minus 1. So that is what is here. On the left side you have s, and on the right side you have sun. Therefore, in Taylor expansion you have the difference between them, and that I'm writing like this. And now the second order terms we have to write in each variable, and then the mixed derivative also you should write. So this is 1 by 2 dou square h by dou s square into s square un minus 1 the whole square plus 1 by 2 dou square h by dou t square into delta tn square will come. So delta Tn square onwards, I will just write it as a small o. Okay, all the expressions, higher order expressions, I will write as a small o. Therefore, I will not go to write dou square h by dou t square. I will observe it in small o. In fact, the mixed derivative also can be observed in the small o, but I will just write and show it to you. Dou t dou s delta Tn s of un minus 1. This also will be observed in the second order term, but I will just write and show you how it goes off. And the rest all are terms which goes slightly faster than delta n square. Like second order term, delta Tn square will definitely go faster than delta Tn, right? So therefore, all the higher order terms, I'm just writing as this notation. And similarly, all the un minus 1 terms also I am writing like. They are also assumed to be very small. Okay. So as n tends to infinity. So that's the second order Taylor expansion up to order 1. Okay. In delta Tn. Okay, this is a second order term, but we will see how they get to have a first order effect. Now we will use, instead of un, we will use this expression un. We have assumed this, right? So we will use this expression in the place of un. We will get, so now I will drop the arguments just for the notational convenience. Hu of t comma s I will not write, just hu, and this h I will bring to the left hand side and write like this, is equal to the right hand side. We have dou h by dou t delta Tn plus dou h by dou s into un minus 1. We already know how un looks like. It is sigma delta Tn square root plus sigma square by 2 delta Tn plus small o of delta Tn. Similarly, plus 1 by 2 delta h square dou s square into the same expression for un minus 1 to the power of square. As I told you, we will also leave this term, we'll club this term into this delta Tn square. Why? Because delta Tn into un, if you see, everybody is having a delta Tn here. So delta Tn into this term will go faster than delta Tn. Therefore, this entire mixed derivative part can be observed into small o of delta Tn, right? So that also we will not write. We will simply write like this: small o of delta Tn plus small o of un minus 1 square as n tends to infinity. So this expression can be rewritten as hu minus h is equal to, I will simply rewrite again. You can see that I am going to write certain things, sigma into s, that is this first part, sigma s delta h by delta s, plus everything else I will use a notation, because in hd similarly there also you will have similar terms. So I will write a notation LH delta Tn plus this order of delta Tn. Everything now, this also can be now using this. You can also write un minus 1 square also in terms of delta Tn, right? Therefore, I will not write this. I will club this also with this expression, where how LH looks like. LH looks like dou h by dou t, because that term is there in the first part. Okay, I have not written here in hu minus d expression. Therefore, that will be observed in this expression, plus sigma square by 2s dou h by dou s, that is the second term. This one, sigma square by 2 into delta Tn term is coming. So all the delta Tn terms I am just clubbing together and calling it as LH, plus sigma square by 2 s square dou square h by dou s square. So this is how hu minus h looks like. Similarly, we can write the same idea you follow and get hd minus h is given by minus sigma s dou H by dou S. There's a root sigma Tn also is sitting here that I forgot to write. Root delta Tn here. So root delta Tn plus LH delta Tn plus small o of delta Tn. Okay, there's only one minus difference here when compared to Hu. So we have these expressions Hu and Hd. Now we have to use it in the expression for Jn. So Jn has Hu and Hd. You substitute that into Jn, we get the following expression. Therefore, recall that Jn H is given by minus 1 plus R into delta T n H plus P n star H U plus 1 minus P n star H D. This can be written as minus R H delta T n plus P n star into H U minus, I'll add and subtract on H, and there is a H D here. P star H D is there minus H D, and since I have subtracted H, I will add one H here plus 1 into H D, that I will put as H D minus, there is a H here, minus 1 into H, that H I will bring here. So now you can see that you have HU minus H, HD minus H are there. So you can substitute these two equations for HUH and HDH. That gives us, the first term is as it is, Pn star into sigma S dou H by dou S root delta Tn plus LH delta Tn plus order of delta Tn, that comes in the first term, minus second term is minus sigma S delta H by delta S root delta Tn plus LH delta Tn plus order of delta Tn, right? And then the last term is going to be minus sigma S delta dou H by dou S root delta Tn plus LH delta Tn plus small order of delta Tn as n tends to infinity. So we also know what is the expression for Pn star. We have also derived that. So let us substitute that in this and then simplify. We get Jn H of T comma S is equal to minus RH delta Tn plus 1 by 2 plus 1 by 2 sigma into R minus sigma square by 2 root delta Tn plus order of root delta Tn into whatever we have after cancelling certain terms. We have 2 sigma S dou H by dou S root delta Tn plus order of delta Tn minus sigma S dou H by dou S root delta Tn plus LH delta Tn plus small o of delta Tn as n tends to infinity. So this can be further simplified to get minus R H delta Tn plus sigma S dou H by dou S root delta Tn plus R minus sigma square by 2 S into dou H by dou S delta Tn minus sigma S dou H by dou S into root delta Tn plus LH delta Tn plus small o of delta Tn. Therefore, the further simplification gives us JNH of T comma S is equal to minus RH delta Tn plus R minus sigma square by 2 S dou H by dou S delta Tn plus LH delta Tn plus the higher order terms. Now put the expression for LH here. We get minus RH delta Tn plus R minus sigma square by 2 S dou H by dou S delta Tn plus that expression we are putting dou H by dou T plus sigma square by 2 S dou H by dou S plus sigma square by 2 S square dou square H by dou S square into delta Tn plus small o of delta Tn as n tends to infinity. And that further simplification gives us Jn del H of T comma S is equal to dou H by dou T plus Rs dou H by dou S plus sigma square by 2 S square dou square H by dou S square delta Tn plus small o of delta Tn as n tends to infinity. Now divide both sides by delta Tn. Delta Tn here delta Tn goes, and this goes slightly faster than a constant, which will anyway go to 0. And then if you take the n tending to infinity physically, limit n tends to infinity, therefore Jn H of T comma S divided by delta Tn will precisely give us, there is a minus RH is forgotten here, delta Tn, that gives us dou H by dou T plus Rs dou H by dou S plus sigma square by 2 S square dou square H by dou S square minus RH. Okay, that is what we wanted to show as LBSH. So this completes the proof of the theorem. This theorem enables us to write the Black-Scholes model in the form of a partial differential equation. So from this theorem, we can say that in the limiting case, the binomial model leads to the PDE dou H by dou T plus sigma square S square by 2 dou square H by dou S square plus Rs dou H by dou S minus RH equal to 0. And this is called Black-Scholes equation. This is also sometimes called Black-Merton-Scholes equation. So the three are well-known economists. In 1970s, Black and Scholes derived the model and tried to apply it in the practical situations. They failed, and then they just published the paper as an academic result. Later, Merton took it up and improvised it, and today this model is widely used in the practical situations with critical limitations. Merton and Scholes received Nobel Prize for this work in 1997. However, Black was not given because by the time Black was not alive. So only Merton and Scholz got the Nobel Prize for this work. We can see that given the terminal value h of capital T comma S, which is given as the payoff for the European option, the equation say 1 to 2 forms a terminal value problem. You can make a change of variable tau is equal to capital T minus small t and x is equal to log s. We can change this terminal value problem to the initial value problem, or otherwise called the Cauchy problem. Dou u by dou t, where u of x comma t is taken as h of t comma s. With this change of variable, after making the change of variable, we will denote h by u, and that gives us r minus sigma square by 2 dou u by dou x plus sigma square by 2 dou square u by dou x square minus r u equal to 0. Tau comma x belongs to 0 comma t cross r, and the initial condition is u of 0 comma x is equal to ht of e power x. X belongs to r, you can write, and this is the initial value problem, and you can see that the equation is a parabolic equation. So it gives us a parabolic Cauchy problem. We can obtain a solution for this Cauchy problem, but it is outside the scope of our course. Therefore, we will not pursue further in this direction. However, I may give you an explicit expression for you and ask you to check whether it is a solution for this Cauchy problem. What you have to do is first put t equal to 0 and see whether it satisfies your initial condition. And then you've given u as a function of t comma x, you differentiate it with respect to t, you differentiate it with respect to x, and twice differentiate it with respect to x. Substitute that into this equation and see that it satisfies. So that is a very easy exercise problem you can do.